So before we actually dive into the slides, I want to kind of provide an opening statement, if you will, of like why should we care about NumPy? Like we have the Python programming language, there's like wonderful things like lists. Why should we care about NumPy, especially when we're doing scientific computing? So our intro here. So NumPy provides multi-dimensional arrays and mathematical operations that we can do on these arrays. So if we think about kind of vanilla Python, if I had two lists here, just ordinary Python, so this is creating a list A and a list B. If I wanted to add these two lists together, this isn't necessarily what we're doing from what we would want from a mathematical standpoint as far as like an element by element addition. This is a concatenation. So if we wanted to do some type of mathematical operation that would add these element by element, we would have to do a for loop or something like this. Right? We like instantiate an empty list. We'd say for value A, comma value B, and zipping these together, we'd say result dot append val A plus val B, or if you know list comprehensions, right, we could have done that. Right, val A plus val B for val A, val B, and zip. Right, so this for loop isn't hard to kind of understand what's going on, right? We're taking each element of A, we're zipping these two together, we're taking each element of A and adding it to each element of B, right? Just that's what we would expect from a mathematical operational standpoint. And the for loop isn't, difficult to write, but it gets tedious. What if we had 3 dimensions, right? What if we had this kind of multi-dimensional array? What if we had all these different things? It's hard for us to, it wouldn't be fun to have to like work through this and type this out by hand. And that's where NumPy comes in. So we traditionally, it's a convention, we usually import NumPy as NP. It's an alias. We can import this library as the alias, the NumPy alias NP. It's like if you were to import pandas as PD or something like that. It's common convention in Python. And what we can do is convert these to arrays. So I should say, I'm going to type some NumPy code for the next 2 or 3 minutes. We are going to cover everything that I cover in this slide, so don't worry if you don't understand it. Again, this is kind of my opening statement, and then we're going to go through all of these things extensively. Okay? So we have this array. And now, when I add these two things together, this actually gives me what I expect. It's not a concatenation anymore. Okay? NumPy, one of the main reasons that it's so powerful is it does something called vectorization. So this for loop is occurring, but NumPy abstracts that away for us, and it actually pushes that down into pre-compiled C code. So NumPy is very, very fast. It sits on top of C. It'll push this down for us, and we don't have to worry about writing for loops when using NumPy arrays. If you're using NumPy and using for loops, it's a little bit of a hint that you might be able to do something better. You should rarely have to use for loops when you're using NumPy. It's because of this idea of vectorization. We'll talk about something later on called broadcasting as well. That's very convenient, where it allows NumPy will do some optimization for us to allow us to define things in one dimensions, and it kind of stretches arrays and adds them together for us. And we'll talk about that in a little bit later on. But this idea of not having to write a for loop, getting that pushed down to C is something that makes NumPy very, very powerful. Okay, so we have this idea, this concept of vectorization. We have this idea of being able to have large multidimensional arrays and do these mathematical element by element manipulations on these arrays. Okay? The other thing that's really nice is we get data types assigned to our arrays. By default on my machine, when I create this array, I have a 64-bit integer or 64-bit float. If you're on Windows, it might say 32. We can change the precision. We'll talk about that in a little bit. But we say that NumPy arrays are type safe. They are homogeneous. They all have to be of the same type. So this makes things efficient as far as a kind of memory allocation where we don't have to do type checking when we're adding things together. We're enforcing a specific type that on the back end, the arrays are assigned that metadata and it's stored there. Now, we'll cover this, but if you notice, my array, NP array, I have 1, 2, 3, these are integers. We'll talk about assignment here. Later on. But I want to introduce this to get it in your heads early on. I'm trying to assign a float here. Maybe I should do it like a 3 or something, 13. So what's happening here is, I'm fumbling over my keys. npa.dtype. There we go. npa. And what I would try to do, so when I created A, I created this as a list of integers, and it stored the data type as an integer 64. What I'm doing here, we'll talk about settings. So Python zero-based indexing, what this is saying is take whatever's at the 0 position of A and set it to the float 3.3456. It truncates this. It doesn't round it. It truncates this because this array has been set up to store 64-bit integers. So we call this type coercion. We'll talk about this in a slide in a little bit, but the point of this in this introduction is to say that these arrays are type safe. They all have to be of the same type. Okay? So if I had my array, font 1, 2, 3, and I declared the data type up front, if I look at my A now and set this, this will come through as expected because my array has been set up to hold floating point values. It's not going to truncate this. Okay? You okay here? Okay. So we have this idea of vectorization. Very, very powerful. We have this idea of having metadata that stores the type of information that our arrays hold. And then we also have something called ufuncs, with a C, not a K. Universal functions. These are functions that have been optimized to perform on NumPy arrays. They perform element by element. So NumPy has a sign function. It has a cosine function. You have these things that we can apply to an array that will function element by element. And we'll talk about this later on. But these are optimized mathematical operations that we can perform on arrays. And we'll talk about a lot of these throughout the course. And then the last thing that I think is helpful for us to understand, or in the kind of opening statement, if I look at the type of what this array is, this is an ND array, n-dimensional. NumPy handles multi-dimensions very, very well, better than kind of your vanilla Python list. So if I had this kind of list of lists, LOL, haha. Okay, this is a list. If I say NP, LOL, it's really not a list of a list. It's a NumPy array. So maybe I should just say NumPy array. If I look at this list, look at this array, if I wanted to grab this 5 here through indexing, using a list, I'd have to say, grab the last, the row at index 1, and then I'd have to say, of that, grab the item at index 1, right? It'd be really nice if we could do something like this and provide some type of just tuple or some type of way to grab this 5 here without having to index twice. And that's what NumPy allows us to do. I could have done this, but that's taking 2 indexes, right? Indexing 1 to get the row at index 1 and then indexing again. This is a more efficient way. It allows us to handle multidimensional data much better. So another reason that we should consider using NumPy is if we have large dimension of data, if you have an X and a Y in a time domain, or maybe you're in 4 dimensions, it gives us the ability to do this in index much easier than with a list over list. Okay, so far? Yep.
Question: when you say it's more efficient to do it with a comma, do you mean more efficient to just type, or is it more computationally efficient because you don't have to do lookup?
Both. So yes, you're saving some keystrokes doing this, but there is this idea of indexing in Python. This isn't just a NumPy thing. This is what we call syntactic sugar, where there's a dunder get item, a dunder set item. And what's happening here is when you have one of these, you're calling that once. That dunder get is calling that on that slice, 1, 1. Here, you're having 2 method calls, essentially. You're selecting the first row, and then of that row, you're also selecting again. So you would have to do that for a list, but in this case, it's computationally more efficient to do it in one shot. So another reason. Let's see, did I lost my link here?
One quick question.
Yep.
What pointed it to LOL there on your last 2 lines?
Sorry.
I might be missing one before.
This one here.
Yeah.
So I said NP array was equal to, I wrapped it. So I created it from the list of lists.
Okay, thanks.
Yep. So there's a scientific Python ecosystem.png that I uploaded here. Has anyone used pandas? Matplotlib? Okay. So the other thing that's really nice about NumPy, this weird kind of pyramid-looking scheme, NumPy, so this is kind of the scientific stack when we think of Python. All these things operate very well together. NumPy, talked about, actually ships with precompiled Fortran and C code. That's why it's really fast. It'll push down some of those for loops in there. But pandas, if you didn't know it, is actually built on top of NumPy arrays. So when you store things in pandas, there's a .to NumPy, or if you call .values, it's going to give you the array back, right? So pandas actually is built on top of NumPy. So all these things interact very well together. So if you're familiar with some of these, the NumPy array is really kind of the base array structure that we use in these other packages as well. So it performs very well and allows us to kind of interact with that throughout.
So in this NumPy array, which is a 2-dimensional array, if I just do one index, it will not give errors. It will use a row, right?
Yes. So we're going to talk about that. So if I say 1 here, it's going to default to giving you that row. Same with the 0. NumPy has this idea of filling in things for us. We can use a colon to do the same thing, but it's inferring essentially what's happening. In a 2-dimensional case, it's going to give you at that index the whole entire row in this case, because that's the 0th dimension. Whereas if it was in 3D, you'd get the 2x2. Same thing. We'll talk about that in the slide coming on, but it's a good observation. We'll talk about how we can use colons and things like that to specify everything. Okay, so just to kind of summarize, one, NumPy arrays are very, very efficient. We have this concept of vectorization and broadcasting. They're type safe, so everything in the array has to be of the same type. We have things called universal functions or ufuncs. And then NumPy arrays also perform very well with multidimensionality. So we are going to, and for these reasons, that's why NumPy is really the standard numerical library for Python. So anytime you do any type of mathematical manipulations or mathematical operations, a lot of times you'll be working with NumPy. So just kind of a lay of the land, what we're going to be talking about today. I'm going to go through a lot of the code that I just typed in detail. We'll talk about kind of what arrays are, how to create them. We'll talk about indexing and slicing arrays, grabbing things out of an array. We'll talk about some of the array calculations that we have available, the universal functions. And then we'll talk a little bit about kind of the data structure, the metadata, how it's stored kind of in the back end, how does NumPy handle memory. And then we'll talk about some more advanced topics like broadcasting and some of the other things like reduce and accumulate and things like that. Okay, so are we okay? Any questions? We're all okay so far? So slide 5, we're going to talk about introducing these arrays, some of this stuff that I've already introduced and covered for you, but when we create an array on slide 5, we have a few ways of doing so. So we're always going to use this np array method or function from NumPy, and we can put in there a list. Okay, so in Python, the list is created with the square brackets. Okay, so I can put a list in the NumPy array function, and that will return an array for me. I can create a list on my own and pass that in, right? That's the same thing as doing the above. And when I look at this array, so again, the type of A, that was because I created it up above. Python has a function called type. I can see the type. In this case, it's an ND array, so ND, n dimensions. We have a data type, which is an integer, 64-bit integer. But I could also, so notice what happens here. You notice a difference between this array and the one I created in 59? That's right. So in this case, when I provided integers to my array, NumPy is going to say, you're inputting integers. Chances are you probably want to store integers. So it's going to default to a 64-bit integer. Here, it's saying, you're providing me floating point values. You probably want to store these as floating point values. So notice, this trips people up sometimes. There's a decimal point here. These are floating point values. So 1.0 in Python is a float. 1 is an integer. 1 dot, no trailing 0 is a float. Okay, so that's why you might notice here, if I were to create this, 1, 2, 3. If I create B as 1 dot, 2 dot, 3 dot.
And if you mix them up, it will be the most precise.
That's right. So what's happening here? Provided an integer, a float, and an integer. Okay.
Wondering when Python says float, you mentioned it might be different between like Mac or Windows and Pro 64 or 32. Does that also mean when I type this code on a Windows versus on a machine, I might have a different device in mind?
As far as precision goes, yes. So you might have 64-bit or 32-bit, but you can set it explicitly by calling the D type or calling as type, and we'll show that in a slide here. So a way that you can solve for that is being explicit upon your creation and not platform dependent.
So it's best practice setting this?
Yeah, because then you understand, you know exactly what you're expecting in that regard.
To set your IDs, it's only integers that are platform dependent.
Thank you.
Floating points are always 64.
Yes.
That matters for precision.
Yes. So NumPy has this idea of a numeric tower or a hierarchy. Right? When I add two integers together, I get an integer back. When I add an integer and a float, I get a float. Okay, so there's this idea of a Boolean will get promoted to an integer, will get promoted to a float, which will get promoted to a complex number. Okay, so if I add an integer and integer together, I'm going to get an integer. If I add an integer and a float together, we have to promote up to a float because the highest, we're adding here and here, it's going to promote up to here to the result. If I added a Boolean and a complex number, it would promote all the way up to a complex number. So that's what's happening here. I have an integer, a float, an integer. It's going to promote all these up to a float for storage. Okay, so if I go back to our slide here, I have a data type. Whoops. We have a n dimension. That tells us our, n dim, number of dimensions. We also have a shape. Okay, so I have 4 elements here. My shape is 4. There's also a item size. So my D type, right, there are 8 bits in 1 byte. Okay, this is 64-bit integers, and I have, that means I have 8 bytes in each item. So the item size tells me how many bytes per item in my array, right? 8 bits is 1 byte. I have 64 bits, so I have 8 bytes. That's where this 8 is coming from. I also have n bytes, which will tell me how many bytes I have in the array. So I have 4 items, each 8 bytes. So I have 32 bytes. This is all metadata that's stored with our array. That's on slide 4. Okay. So slide 5, I'm going to create 2, well, I guess I should say, if I look at A, right, I have 0, 1, 2, 3. We're familiar with the range function in Python. You've seen this before? Whoops. We can create NumPy arrays using the range function. We can also use a range, which stands for an array range. So if you didn't want to type out 0, 1, 2, 3, right, you can use range. We could also say provide a step size. Whoops. Start, end, and a step. Start, stop. Thanks. You didn't want to have to type all this out. There's ways to do this. So a range, array range is that function. Okay? The other thing that's nice about the arrange function is, notice the difference between this and this. It's going to infer the type that you want back based on how you provide the start, stop, and end here. So I'm providing an integer 5 here. It's going to give me integers back. Providing a float here. It's going to give me floating point numbers back. Slide 6. So I'm going to create these two arrays. I have A. I have B. We can do mathematical operations through vectorization. It's always going to be applied element by element. So we saw A plus B is always going to put these together element by element wise, right? So 1 plus 2 is 3, 2 plus 3 is 5, 2 plus 4 is 7, right? We can also do multiplication. We can also do a power. So I'm going to create an array of floating point values here, x, whoops, a range, not array. So the other thing too is, so Python is, any MATLAB users? Python is 0-based indexed. MATLAB starts at 1, right? Yeah. So Python is 0-based indexed. So you can think of this as up to, but not including the stop value. It's a start at 0, go up to, but not including 11, which is why you're going from 0 to 10. Zero-based indexing for a number of reasons. One is the number that you provide is the number of elements you're actually going to get. So 0 to 10 gives you 11 elements, essentially. Okay, so I have our x here. NumPy has a lot of constants. So you have pi, Euler's number. Some of these are constants. But if I save a scalar c as 2 divided by, or 2 times, np.pi divided by 10, I have a scalar value here. If I multiply x by c, what's happening is it's broadcasting this scalar value. So what we don't have to do is we don't have to create a C array that has the same number of elements as x and then multiply in order to get this. NumPy does that on the back end for us, where we can just take this x array that has 11 elements, multiply by that scalar, and it's going to multiply each one of these for us. So we don't have to create that array of 11 elements for C. We can just allow it to do it on the back end for us. So if I wanted to set x, it's x times c. Right? So if I want to update x in place and say, take the x array, multiply it by c, and store that as x, I could do this, right? I could say x equals x times c. Or I could use what we call an augmented operator. I could say x times equal to c. Okay. This here works with addition, subtraction, division, multiplication, all these things. We okay here? Okay. And then, like I said before.
One of the areas still, the values of the area are still the same.
Here?
Yeah.
It's because I did x times c here. And I stored this. I didn't update this. I didn't say x equals.
Okay. Oh, sorry.
And then I can take the sign. Right, we talked about the universal function here where you take a sign, do these things. Okay, any questions? So slide 7. Might be a little bit easier to draw here. So we talk about setting or indexing arrays. We'll talk about slicing in a bit. But again, Python is 0-based indexed. So if we have an array of 0, 1, 2, 3, our index starts at 0. And if I want to say A, 0, we talked about this square bracket is how we index or grab from the array. That's going to come to the 0th index and give me what is there. We can set or assign using the same syntax. So we're saying, where is index 0? Set that to 10. Now we talked about this. We have to be careful here. If our array A was set up to hold integers at the onset, if we tried to assign 10.6, a floating point value, into that array, it's going to truncate this. It's not going to round it. It's going to truncate it. Only take the integer portion and store it into the array. There's a fill behavior. So there's a method called fill where if you have an existing array and you want to fill it with values, it's going to do the same thing as that type coercion where it's only going to take the integer portion here. So we have this array A, and we're saying we want to fill this with negative 4.8, but because we set up A to hold integers, it's going to truncate that and fill it in there. If we didn't want this behavior, do we know how we would, if we wanted to be able to store floating point values, how would we do that? So there's a few different ways. Okay, I provided integers here. I can say a dot as type. Okay, so if I have an existing array, A, and I want to change its type, I can say dot as type and save that as a new array. Or at time of creation, I can provide the D type. So there's also yeah. Whoops. So you can provide this, right? You have it. You can provide these as well if you wanted to. I'm just being lazy and not typing out the extra. It works for integers as well. So you'll notice here, I typed float. I don't think, oh, I can, that does work. So you can do a string or the actual NumPy object here. Provide that if you want to. Okay. Okay, here. So slide 8, talking a little bit about multidimensional arrays. So here we have this list of lists. Pictorially, we have this 2D array here. When we say a.shape, it gives this to us in terms of dimensions. So the first dimension here is a 2. It's dimension 0. We have 2 rows. Our second dimension 4. We have 4 columns. Now, it's important here to understand kind of what's happening, because when we start doing mathematical operations, we can, if I said that I wanted the sum of this array, there's 4 different ways I could calculate that sum. 3 different ways I could calculate that sum. could sum every single value in that array, right? Or I could say sum across my columns, 1 per row. Or I could say sum across my rows, 1 per column. So there's 3 different ways I can calculate a sum. And the way we tell NumPy how we want to do that is using something called axes, or an axis, providing an axis. Those axes correspond to these dimensions. And we'll talk about that later on when we start getting into some of these mathematical operations. So if I wanted to sum, the challenging part is the more dimensions you add, you're always going to add to the beginning of your shape. And as you add to the beginning of your shape, your dimension, whatever your dimension is, you're going to add 1 to it. So what do I mean by that? It's a little bit confusing. So if I had I keep doing that. I have 25 values here. My dimension is 1. Maybe I should use 24. My dimension is 1. My shape is 24. I only have 1 dimension here. This would be the 0th dimension. Right? My shape is 24. What's at the location? 0 in my shape tuple, 24, 0. If I reshape this, and we'll talk about reshape. I have 6 rows, 4 columns, 2 dimensions. Whoops. The rows are my 0th. The columns are my 1th. So if you think about the shape, right, we had 6, 4. I want to go across my rows. I'd specify this dimension. If I want to go across my columns, I'd have this dimension here. Okay, so we're adding to the front. When we're adding dimensionality, we're adding to the front, and we're adding 1 to each dimension. It's still confusing, hazy. Better example? Do we need another example? Okay, another example. A is we have A. This is our shape of A. It's 5. If I reshape this to be 1 by 5, so my original A, notice the brackets here, right? It's only 1 dimension, 5 comma. When I reshape this, there's 2 brackets here. So this is like I have 2 dimensions, but I only have 1 row, right? 2 dimensions, but 1 row or 5 columns is different than just having 5 values, a vector of 5 values. When I reshape this and add 1 to the beginning, that shape becomes 1, 5. I'm adding my 0th dimension now is my rows, and my 1 dimension is my columns. Whereas here, I only have a 0th dimension. I don't have more than 1. It's just 0. This will make more sense when we get into multidimensionality and specifying. But what I mean is, if I have this A, there's only 1 dimension. If I say dot sum axis equals 0, there is no axis 1 on this array, this A array. Whereas if I reshape this, if I sum this on my axis equals 0, and I sum this on my axis equals 1, what's happening here is my A is now multidimensional. My 0th axis is no longer across, now it's down because I have 2 dimensions. So when I sum on my 0th axis, it's just summing down here, which is just giving me one array back down. Now when I have my axis across 1, because I'm in 2 dimensions, it's going to sum these values across and give me my 10. I promise this will make a little bit more sense in a little bit, but clear as mud for now, right? Okay? Okay. So we have this shape. The number of dimensions is important. It's how we're going to start doing our mathematical operations. There's some more kind of metadata. The size, you just think of those as like the number of cells we have in our array. It's the shape, the product of the shape. Right? So if I was 4 by 2, I have 8 elements, right? And then we can get our dimensions. Indexing behaves much the same way, but now we have to specify these in order of our shape or our dimensions. Right? So dimension 0 going down, we're saying 1, which is this row here. Right? So 0, 1. We're specifying a 1 here, which says grab in the 0th dimension that row. And then this 3 specifies this dimension, which is this dimension here, 0, 1, 2, 3. And that gives us this 13 here. So that's what's happening when we index.
Where's the 13?
Right here in our array. And it returned it here. We can set as well, multi-dimensions, right? 1, 3, we want to set that to -1. And that will override that 13 in our array and make it a -1. Now, there was a comment made earlier that said, hey, if I say A1 in the multidimensional case, it doesn't fail. It gives me this whole entire row. What's happening is NumPy is going to, by default, give you everything in the 0th dimension if you only specify that one value. So what's happening here is because we're only specifying 1 here, our 0th dimension is going down. So it's going to give you this entire row here, the 0th dimension. It's like saying with a colon, give me everything. Okay. So a lot of times, I'm going to code this live. I guess I should say this now. So sometimes in NumPy, we'll get this behavior where we get like a lot of decimal places, or we get scientific notation, and we might not want that. We just want to see like some rounded values or things. There's ways to change the display, so how the array is displayed coming back to us. This does not change how the data is stored in memory. This only changes the display. So this is only like coming to you as the developer, as the person wanting access to that. So if we have this array, I'm going to go from 0 or 1 to 3 by 0.5. If I multiply this by pi, if I multiply this by a really large value of pi, or a really small value as well. So we have 8 decimal points here. We see that we have scientific notation by default. There are 2 ways to do this. You can set the formatting. If you set the formatting, you have to remember what the default was, because you have to go back and set it to the default. So you can get the defaults, set it, and then set it back to the default. Or you can use something what we call a context manager. If you've ever tried to open a file in Python, you might have used the with statement, right? Like with open the file name as fp : something. We call that a context manager. So we can do the same thing here. So I'm going to show you both ways. If I get print options, so this tells me some things about how NumPy is going to print the output. this precision and this suppress are the two things that we're concerned about in order to change the way we have scientific notation and the decimal value. So this 8 is the fact that we have 1, 2, 3, 4, 5, 6, 7, 8 decimals, and suppress false means it's not going to suppress the kind of scientific notation. So I can say NP, so I have to use get options if I didn't know that it was 8 and false by default, right? NP.set options. I can say precision is 2. Oops. Set print options. And now if I look at my array A and I say NP, whoops, A times my pi, you'll see that I only have 2 decimal points here, whereas before I had that 8, right? If I did A times NP dot pi times 1 e to the 8, -6, right? Still get scientific notation, but only 2 decimals. And I can say np.set print options here. Suppress is true. PP. And then if I did A times np.pi times 1 e to the -6, those are zeros because this is a very, very small value, and it's not going to give me the scientific notation. So I'd have to go back and set these again. And now if I do all that over again, we'll see if I get the original value. If I wanted, go ahead.
Yep. And you said that changing the print option doesn't change what's stored in memory, right? So if I were to do an operation with a different array, it would use the longer,
Correct. Correct. Yep. So that the multiplication, all that stuff, it's stored on the back end. This is print options. So the way it's displayed. Yep. Now, if you're like me and you're worried that it might, mess some stuff up, and you want to be able to retain things to kind of double check, the way I do this is with a context manager, and I'd say with np.print options. So notice here, not set print options, but with np.print options. And then we'll say A times np.pi. Whoops, print. I want to print this. And then I can still access this outside. If I get my print options, nothing's changed. Right, so this is a little convenient way to just display things nicely, but still have access to the default behavior without actually having to go in and set, reset, all that stuff. Again, just kind of a convenience to know about. You okay here? Questions? Go ahead.
Go back to the multi-dimensional array. Can you tell me the list of these, or can you also dictionary?
So your dictionary, the problem with a dictionary, well, not problem, but if I have a dictionary, notice what happens here. It's taking the whole entire object as my dictionary. So like, A0, I can't index this. That's weird. Normally what you'd want to do is something like dot keys or dot values, and that'll grab the actual like things from, this is probably, you want to convert this to a list. Again, it's a list, but it's going to retain the actual like object that you provided. Usually when you're dealing with NumPy arrays, right, you want like the numerical, probably not like the keys, you probably want the values. But I think like from pandas, if you're using pandas, I think there's like a dot from dictionary or something to read it in as a data frame. I don't think there's a NumPy dot from dictionary. Okay. All right, we're on slide 10. We're going to talk about indexing and slicing. So we've introduced this idea of indexing where we can grab, one row or one item. There's also a concept of kind of slicing where maybe we want like a patch of data. We have this big array and we want to grab some patch or some field or like more than just like one value, one row, things like that. We can do that through slicing. So mathematically, the way we provide these is kind of like what we showed with the range function. We have a lower or a starting value, you have an upper, and you have a step value. And they're separated by colons. Mathematically, this is up to but not including the upper. So lower all the way up to but not including the upper value mathematically here. That's what this looks like. And the step tells us, like it's like a stride, if we're familiar with that term, right? Like 1 or 2, how many we have. Now NumPy, like Python, the default, if you don't specify a lower, it's going to assume that you want to start at 0, or the starting point. If you don't provide an upper, it's going to assume that you want to go to the end. And if you don't provide a step, it's going to assume that you want a stride or a step size of 1. So if we have this array, I'll do this in code so we can see this. So we'll do this slide and then we're going to take a break. So slide 11. So I have this array. 10, 11, 12, 13, 14. The indices for this array, right, are 0, 1, 2, 3, 4. So if I said A4, we're going to say A2. We also have negative indices. Starting at -1, so counting from the back. Okay, so I can provide positive integers going from left to right, 0, 1, 2, 3, 4, or I can count from the back using negative, -1, -2, -3, -4. It's helpful to use negatives. Sometimes it describes intent. Right, so if I had this array A, and I said A3, that tells me, that communicates to me, grab what's at the third index. Right? It doesn't really communicate to me the second from the last. Right? I'd have to know that this array was a shape 5 in order for you to say, hey, A3 means the second to last one. Whereas this describes more intent for me. So you'll see something like, oh, grab the second to last one, or grab the last one in the list. I'd have to know that this list had 5 elements in it in order to say A4 is the last one, right? If this had 10 elements, A4 isn't the last one, but A -1 will always be the last one in my array. Okay, so we have these negative indices. Sometimes it makes more sense to count from the back than it does counting forward. So when we come back from our break, we'll talk about how we can kind of mix these together. Using strings. Yes, and we'll talk about that. So there's I'll end with this. So I have A. So we'll think about why is this true? Why does this work? Okay, we're going to go ahead and get started. Okay, so we are on slide 11. Did we think about why? So why does : -1? So I go back to, so we have an array A. Why does this work? And why does it print from the back forward? Very good.
That's not important.
Yep, that's right. So if we go back to our slides, when we slice, so this variable is like an array. When we slice, we have a lower separated by a colon, an upper separated by a colon, and the step size. If we do not specify any of these, there's default values. The default for lower is 0, or start at the beginning. The default value for upper is go to the end of the array. And the default for the step is 1. So in this case, we said colon, colon, -1, which means start at the beginning, go to the end, but reverse my step size, go backwards. Make sense? Good? So we can also specify, so we can, how do I want to say this? We can mix and match a little bit. So I can say go to, I can say start at the 1th, right? So start at 1, go up to but not including the third index. So start here, 1, 2, up to but not including this one, so I just get 11 and 12. I can say -2 here, right? So counting from the back, -1, -2. Oops, sorry. -1, -2, up to but not including that. So that's 11 and 12 as well. I could say -4 to 3 as well. -1, -2, -3, -4, up to 3, up to but not including. Now a positive index, so a positive index tells us that we're always going to count in our original array from left to right. From left to right. A positive integer as our step is always going to tell us that we're counting from left to right in our original array data. So if I said from -3 to this is going to give me an empty array because I'm trying to count from right to left, right? I'm trying to go from -1, -2, -3 to -4, from right to left. But I've specified a positive step size as 1. If I really wanted to go from, if I really wanted 12 to 11, I'd need to put a negative step size here. And the negative step size tells me that I can read in the original from right to left. Okay? If I wanted to grab things from like the second element on, I can provide just a start. That'll say, right, again, I have 2 colon. So I've said start at 2, and then colon for these. Go to the end, step size of 1, all the way to the end. Step size also works with, right, every other one, stride of 2. Okay here? So we can start getting into kind of these more complex slicing, if you will, where we can start providing patterns of how we want to grab things from our array. So remember, we have 2 dimensions here, 0 and 1, dimension 0, dimension 1. So whatever I provide, right, when I'm slicing, this is the dimension 0, this is dimension 1, separated by a comma. So in this case, if I color code this in orange, this is saying the 0th row. And this is saying start at index 3, up to but not including index 5. So I get 3, 4 here. Okay, this blue, this says row 4 and on. So start at index 4, 4 and on to the end of my array. And then 4 and on in terms of my columns. So that overlap are these 4 values here. Okay. So this colon here, when we use a colon, we use colon to separate our slices, but we can also use a colon as a single. So notice this is the whole entire thing. This is telling me all the things. That meme, right? Like, give me all the things. Everything in that dimension is what that colon means. So this is saying all the rows, but I only want the second column. Just give me all of these. Okay? And then this last one, we can take a strided view as well. So we're saying this is an actual slice. So start at index 2, every other in terms of the rows. And this is all of the columns, but by every other. So this one, this one, and this one. And that overlap are these values here. Okay? Any questions here? Okay. When we start to talk about slicing, NumPy does something as a bit of a memory optimization for us, where when we slice certain things, they're referencing the same locations in memory. We'll talk about that in a little bit. When we slice things, we create something called a view, not a copy of an array. So I'm going to introduce this topic. We're going to talk about it in detail in the coming slides. But just know, keep that in your mind as a little reminder, slices create views, not copies. What that means is, if we have a larger array, we take a slice. So we have an array A, millions of data points. We filter it using a slice or indexing to array B. If we alter things in B, it's also going to alter things in A because they're pointing to the same reference, the memory reference, the same pointer. We can create copies, or we can do something called fancy indexing, which will always create a copy. But for us, NumPy is going to try to be a little bit memory efficient and not just create copies of data everywhere when we can reference the same memory as a view. We'll talk about that in the next few slides. But we can set, so we've sliced this data, right? So this is -5, -5, -4, -3, -2, oh, that's wrong. -1, -2, -3, -4, -5. In terms of the negative index, so I say I want -2 and on, that gives me that 3 and 4. But I can assign that values. And that'll put it in here and replace that 3 and 4 with a -1 and 2. So just like we've seen before, we can set these. What I cannot do is I can't set this. So if I said, let me show you instead of actually telling you what's going to happen. If I said A, -2 on, gives me that 3 and the 4. I can set that as -42, -42. That's going to override those for me. It's going to set those values. I cannot say 1, 2, 3 here. The shapes don't match. So I'm trying to grab something that's only 2 elements long, and I'm providing 3 elements. So it's not going to be able to save that in there for me. But I can use a scalar and that will stretch it across all those for me and fill all of them in. Okay, so the shape has to match unless you're just providing a scalar, and it'll fill it in for all of those, right? Because this is 2 values here, the last 2 elements. Do something like that. Okay? All right. Throughout the course, we have some exercises. Some of them are called give it a tries. Some of them are going to be longer exercises. I want to give you the opportunity to practice using slicing and indexing. There's 2 ways you can do this. You can have your IPython console open, right? And you can type a is equal to np.range 25. That creates 25 values. And then you can reshape that. Do a 5 by 5 array. You can type that if you want, or if you're in the right directory, if you go, there's a give underscore it underscore a underscore try, give it a try directory. There's a notebook in there. Open that notebook. These exercises are also in there with the boilerplate code for you. So we run the first cell with a shift enter. I'll import NumPy. The image is there for you. You can run this. Put your code in here. All of these have solutions. So there's a little solution tab here. If you click where it says that bold solution, it's going to toggle that solution for you. Okay? I highly recommend that you try it on your own. Do some practice before looking at the solution. But if you get stuck, no shame in looking at the solution for some help. Okay, the bottom, so on the slides it's orange. In here it's yellow. I would say in order, if you want to try to go easy to hard, I'd go yellow or orange on the slides. Yellow, red, blue. Yellow, red, blue. Easiest to hardest. Okay, so let's take 5 minutes. We'll do this, and then we'll review as a class. Okay, we have about 15 seconds left. Is there anyone that needs more time or would like more time? It's okay. More time? Ready to review? Okay, we'll go ahead and review. Who got all of them? Who was able to get all of them? Good job. All right. Good job. I wish I had something to hand out. I'll give you a round of applause. Okay, so we're going to start with the orange or the yellow, however you want to think about it on the slides. But we have our A. What we need is our last row here. Now there's a few different ways to do this. If I knew, right, I knew that I had 5, if it was 5 by 5, and I wanted to grab the last row, I could say A4. That works. It's fine. I could also say A-1. There's also what we could do is we could say I want the last row and all of the columns, or I could say the 4th row and all of the columns. For me personally, because I know A has 2 dimensions, this communicates to me that I want the last row, and A is a multidimensional array. Okay? If I told you this, what would you expect to get back there without knowing A? This could be a single number, or it could be a row of numbers, depending on the dimensionality of A, right? So sometimes if you're trying to communicate intent, it's helpful to add that colon to say that you're multidimensional, right? Because if my A was just that just gives me a number back, integer. Whereas in our case, when A is multidimensional, we're getting an array back. Right? So sometimes this is helpful to be able to show intent by including that colon. Okay? Next one is, we'll do red. The way I like to, so let's clear this. the way I like to kind of set this up is if I know that I'm going to do slicing, I'll set up my, you don't need this much white space, but I'm doing it so that we can see it. I know that I'm going to have to slice this array given the red, those columns. So the first thing I ask myself, in this case, I have 2 dimensions. Do I need to slice my rows for red? Let's look at red. Do I need to slice my rows? No. So what should I put in that first dimension? I heard it? A colon. That's right. So I don't need to slice my rows, right? So I'm going to put a colon here. Okay? Now, when I look at this, I say, okay, there's some pattern here that's skipping columns, so I know I'm probably going to have a step size. So I would just try to say every other one and see what that looks like. Right? So we do that by from start to end with a step size of 2. Let's just see what that looks like. Well, that's kind of the inverse of what we want, right? So I'm starting at 0, going to the end, doing every other. Let's start at the first one and do every other. Okay, go ahead.
I don't really understand why we need comma sometimes and sometimes we don't. It seems that parameters are separated by a colon, right? So why is there a comma sometimes and sometimes not?
So the way you specify a slice, so there's a little bit of, there's a few things that we can get confused on, and that's fine. When we specify a slice, we use colons to separate our stop end, our lower, our upper, and our step. So these colons are at an axis or a dimension level, right? So when I have A separated here, I'm specifying dimension 0 and dimension 1, and this in here can be a slice. This is a slice. This slice notation in here. This comma is telling me if I want to define what's in dimension 1 or multiple dimensions. If I have more than one dimension, this comma is separating the slices that I want over those dimensions. So if I had 3 dimensions, I'd have to have comma, comma here, and then provide things here. If I do not provide any of these commas, it's going to grab what's at my dimension 0 and give that back to me. Mm-hmm. Okay here? So for red, I have all of my rows, the colon, start at index 0 and go every other. Or I'm sorry, start at index 1 and go every other. Okay, let's look at, I was drawing, sorry. Let's look at blue. Question?
Yeah, so when you have that double colon, so like 1 colon colon 2 for red, you could theoretically just specify the end of that slice, right, as like 4 or something, like 1 colon 4 colon 2, would that be the same?
And why does putting a 4 there work the same as just doing this?
Because it's like 2 to n.
Right. There's 4 there. So again, this to me communicates go to the end of the array, all the way to the end. This to me communicates go up to but not including the 4th column, right? Or in that direction, yeah. Okay, so let's look at blue. Do I need to slice my rows for blue? Yes, I do. For me, I'm going to start the same way that I did before. Let's just start with a step size of 2. Maybe we'll get lucky, and that's what we want, right? So let's do a colon, colon 2, and look at that. Now, to answer your question here, notice I'm including the comma here. I'm not putting anything there. It's the same thing as if I would have said A colon, colon 2, because it's not specifying anything. It's assuming that I want everything in that dimension. So these rows are not the rows that I want. Again, it's kind of the inverse. So I'm going to start at 1. These are the rows that I now want. Do I need to slice my columns? Yes. So let's try : 2. That's almost right, but I'm including the last one. I don't want to include the last column. I want to go up to, but not including the last one. Or this. Or this. Okay, I would use this. This to me communicates that I want to go up to, not including the last column, every other. Okay here? Good? Okay. So we also have something called fancy indexing. And before we get into fancy indexing, I want to highlight the fact that we do have something called, these are called slices. We're creating views here. And this is what I was getting into when we talk about the memory management, pointing to the same kind of reference. When I create, so I'm on slide 15, I'm going to slide 15. When I create this array, when I create B as a slice of A, okay, we agree that this is a slice. I'm using the slice notation. 2 up to, not including index 4. If I say B of 0 is 99, well, that makes sense. You just set the first item of B. Uh-oh. This makes some people feel not so good. Well, what's happening is when we create a slice, we're sharing memory. And altering the slice alters the parent as well. We can check this. There's a shares memory function. If those two arrays share memory, if you want to say, I don't remember how I created this array. I want a quick shorthand to see if I alter this array, it's going to alter the other one. This is a nice, helpful shorthand. The theorist would say, well, you should remember you're creating a slice, so you're creating a view. I'll say this is a handy practical approach to trying to check whether or not you're sharing memory. Now, we can explicitly create a copy, and this won't be true. So if I say C is still a slice, but I'm using a .copy method, right? Here's C. It's because, well, maybe this would be a better example. Here's my C. Here's my A. If I do the same thing that I did before, whoops. C gets altered. A does not. They do not share memory because I explicitly called .copy. Okay, so if you want this behavior, you can call a .copy. Anytime you create a slice, by default, it's going to create a view. NumPy is trying to be efficient here, where it doesn't want to try to keep copying the same information that it already has stored. Okay, this can be good or bad, depending on what behavior you want. It's something to be aware of. Okay, so we can call it .copy. There's also something called fancy indexing that we'll get into. So fancy indexing will always create a copy. Fancy indexing, we can fancy index in two ways. We can create a Boolean mask and specifically describe, based on that mask, how we want to pull things from an array. So if we had a mathematical operation where we said A is greater than 5, that'll give us a Boolean mask back, and we can use that to then filter A. So I can say something like this. and we'll get into this, is Boolean masking, or I can explicitly provide not a slice, but the indices that I want to grab as a list, not as a tuple. So if I say 1, 2 from A, notice this is not 1, there's an extra list in here. I'm providing the indices as a list. This fancy indexing, so if I said D is equal to A, 1, 2, this is D, this is A. This is fancy indexing, providing a list of indices that I want to grab. It will not create a view, it'll create a copy, a different array. Same thing if I said, running out of letters here. These will not share memory. Okay, so sometimes if you're not aware of this, it can cause some major issues. Whenever you do a slice, remember it's referring to the same data as its originating array, the parent array. If you don't want that behavior, you can explicitly call it .copy. You can use fancy indexing if you want. Okay here? Go ahead.
So the difference between regular and fancy indexing is just this memory handling, or is there more to it?
So we're going to talk about how NumPy stores data on the back end later on. In memory world, there's no concept of like a multidimensional array, right? You can think of it as almost like tape, where it's like it starts on this memory like tape and then writes data and you're pointing to that address, right? So this array, like a 5x5 array or something, it's not like 5x5 stored in memory. If we can do things in NumPy that can access that same data, but just change the way we access it, like changing the strides or changing the shape. This is why a transpose is very, very efficient, because it's just swapping the axes and swapping the strides. It's the same data buffer, you're just swapping things. If you can't do that, so the way you think about a slice, you can describe it almost as like a pattern in your data. Every other one, start here, go every other, stop here. It's a pattern that can point to the same data because there's a predefined pattern that you can use to understand what you're grabbing. Fancy indexing is used to grab things that might not have that type of pattern. So you might want to grab the first and the second and then the eighth. Like there's no way to describe that saying start here, go every other one. There's no pattern for that. So the reason that fancy indexing creates a copy in memory is because there's no way to access that same memory using a different pattern. You have to create a whole new kind of memory buffer or something like that. It can't access the same data and just rearrange some of the metadata to get you back what you're trying to do. Okay, so fancy indexing on slide 16. If we have an array, 0 to 80 by 10, right? So 10, 20, 30, 40, 50, 60, 70. I can provide indices here. So my indices is a list. And if I say 1, 2, -3, I can index based on these indices, right? So 0, 1, and 2, and then -3, -1, -2, -3. There's no real pattern that I can describe here. If I were to say like A every other 2 or something, like I can't get what I actually want, that 10, 20, 50, right? There's no predefined like pattern, so I can't take a slice. We'll use something called fancy indexing here. Now you don't have to like predefine your list. I could have said 1, 2, -3, but it's easier to see that that's actually a list by defining it before. I can set using fancy indexing as well. So that has now set those values to 99 at those indices using fancy indexing. So this is based off of, so fancy indexing using indices as a list. So that's one way to fancy index. The other way is creating a Boolean mask. So I can create this mask, 1, 0, 1, 0. Now I'm doing this, it's a little bit different than what we normally do this as. So in Python, Booleans actually get treated as integers. So when I create an array of zeros and ones and tell it that the data type is an integer, it's going to convert those to actual integer values of true and false. If I create this mask and filter A by that mask, whoops, this needs to be another one. So this is my mask. What did I do here? What is A? Oh, A is a lot longer than that. Let's just do some 1, 2, 3. Okay. Here's my A. Here's my mask. If I filter A, or I should say index A by my mask, it's going to give me only the values where this is true. Right, so true for 0. Don't give me this 99. True for this 99, no 30, and a 40, and then false for the rest. Now I created a mask shorthand. We usually don't create masks this way. We usually create masks by some filtering operation, right? So if I have A, I say A is greater than 20. This creates that Boolean mask for me where I want to filter, where I don't have to do it by hand. I don't have to look at my original array and type out ones and zeros and things like that. Okay, so I can take this, I can say my mask is equal to A greater than 20. Then I can say, whoops, filter based on that mask. Or I could just put that in as well. I don't have to create a separate variable mask if I don't want to. I can just put it in. So fancy indexing, providing indices, providing a Boolean mask. In 2 dimensions, we can combine these. So I could say in my dimension 0, I could provide a list of indices, and in my dimension 1, I could provide a Boolean mask if I wanted to. And that's what's happening on slide 17. Are we okay here? Yes?
So the term fancy indexing is well established, but just occurred to me when you were showing this, it might be more useful to talk about the slices as being regular indexing, and what we're calling fancy as being irregular indexing, because that's what's different about it, is that slices, you always have to pick something that's regular, like the step size is always the same all the way across. But with the Boolean and integer array indexing, it doesn't have to fit. So irregular might have been a much better word.
Yes, that's a great point. That's a great point.
When you're doing Boolean and you say that your mask is A greater than
Mhm.
20, and then A is that mask.
Yep.
That, so A refers to both the array and individual elements.
So that's a good question. So what's happening here, so I have A. A is our array, right? We've seen where if I had another array B, right, I could add A and B together if B was an array. We've seen that. We can not only apply mathematical operations to array, but also logical operations. So this idea of like a logical and or a logical or like a greater than or a less than or something. What this is going to do is vectorize that logical expression across everything in our array. Just like when we were adding things together, it was doing it element by element. So what this is going to do is look at my array A, and for every element in A, ask the question, is it greater than 20? And then provide a Boolean result there. So either a false or a true. Then what I'm doing is I'm treating this kind of like saying this is mask. Saying mask equals a greater than 20, and then I'm passing that mask into my filter, my a selection. So I could have said, this is shorthand. I could have said things like true, false. Like I could have provided those true and false values in there myself as an array, or I could have saved this as a mask, or I could have put that in where this expression I had saved as this before. Sorry, this is a shorthand. I shouldn't have done that. In IPython, so there's, in Python, underscores have meaning. Okay, we have this idea of like dunder methods, they're special methods. In IPython, the underscore is a reference to the output of the previous command. So what I did there, so if I said 5, I could have done this. It's taking the previous command and referencing it. So when I said a greater than 20, I said mask is equal to underscore. I should have just said mask is equal to a greater than 20. I was being lazy. That's what's happening there. Does that answer your question about the a? Okay. Go ahead.
Is there also an example of equals equals? Because I could be surprised.
It's a good. So we did equals equals here. We have something like this. If you have an array A, and I had array B, whoops. That will broadcast that. There's an example that I'm drawing a blank on that. This right? Okay. I'm gonna have to come back to that as an example later on. Go ahead.
How do you do like, let's say a greater than 50 less than?
So you have this. So in Python, you're getting at something like this. We can string these together. But what's happening here is we get a, we need to do some type of bitwise operator. Essentially what we'd need to do, there's probably a better way to do this. There's an and bitwise. So sometimes in Python you have an and. So what's happening behind the scenes when you're trying to do this, this might have been what you were getting at, but maybe not. Underneath the hood, Python's going to try to access this and. But what's happening is we have this array. So this gives us an output, an array output. This also gives us an array output. And it doesn't know how to, what's the truthiness of the actual array object. So you're saying array and array. Really what we want is this to be vectorized. So we want to say for each of these elements here, and each of these elements here, put them together and give me the logical and. And it doesn't do that under the hood. But the bitwise operator, so Python has bitwise operator, the ampersand is and, the pipe is or, the caret is exclusive or. But what that does is that does what we actually want, is it stacks these kind of on top of each other and calculates that value.
As another gotcha, the obsolete parentheses.
Yes. Okay. So slide 17. What's happening here, I'm going to draw on this and then I'll code it up because there's something that we can do that helps me at least think about this. Remember we have dimensions, right? So this is dimension 0. This is dimension 1. What's happening here in fancy indexing is we're providing a list of the row indices and a list of the column indices that we want. So you can think about these as being zipped together in the coordinate system of your array. So this is saying row 0, column 1. Row 0, column 1, which is this value here. Row 1, column 2. Row 2, column 3. Row 3, column 4. Row 4, column 5. So we're providing indices here. Irregular. It's diagonal. Okay, so a few things. One is so we want A is 6. Oops. What do I want to do here? Need to reshape this. There we go. That's backwards. Okay. Really what's happening here is when we provide indexes, fancy indexes, what I like to do is say, okay, what rows do I want? So I want rows 0, 1, 2, 3, and 4. What columns do I want? In conjunction with those, we want 1, 2, 3, 4, 5. So our indices, it really look something like this. If I look at A, I want the coordinate like system as terms of the dimensions in our array, 0 and 1. If I look at my rows, whoops. Rows, columns, A. Okay, let's try this again. Rows, columns, A. If I stack these and zip them on top of each other, right, to get the actual coordinates that I want in this array, that's kind of how you can think about providing indices for your fancy indexing. Where 0, 1 pertains to my 0 dimension is this way, my 1 dimension is this way, so 0, 1 is my 0th row and my 1th column. 12, 23, 34, 45 to get diagonal. Now if you want to cheat, there is a diagonal and you can provide an offset. You can do that as well. But the point of this is to display fancy indexing where you're providing indices. Now blue here, what's happening in the blue is we're saying start at row 3 and on, right? 3 comma, or 3 colon I should say. Row 3 on, and then providing a list of indices, 0, 2, 5. We don't have a regular spacing. We can't slice here because we're doing, every other one would give us this row. So we can do 0 column, 2 column, 5 column. 0, 2, 5. This last one, we're creating this Boolean mask where these are getting, 1s get evaluated to true, 0s get evaluated to false. So if we put that mask in terms of the 0th dimension, true, false, true, false, false, true, all of which get applied to the second column, which gives us 2, 22, 52. So if another give it a try, this is also in the notebook. So if you open that notebook again, scroll down a little bit, should have the same data there for you. There's two different ways you can do this. So there's two questions. One, get all the blue items. You can go from top to bottom, right? So if you went from top to bottom, you'd get 3, 6, 10, and 19 as your result. You can also go from left to right, where you get 10, 6, 3, 19. I'll do both of them, but pick one of them. You don't have to do both. Pick one of them, either top to bottom or left to right. Depends how you're defining your indices. And then the second part is to get everything that's divisible by 3. There's a modulo. Are we familiar with this? Do we know what modulo? You know this? Remainder, right? In Python, do we know what the modulo is? Yes, percent. So 25 mod 5 is 0. 25 mod 4, whoops, is 1. Some of you might not know, but there's also a div mod, which actually gives you both, which is pretty cool. So the remainder is the last one. But modulo is what you want to use. Hint, hint, for part 2. Okay, so we'll take 5 minutes. If you need help or have a question, so there is a solution for this one as well. Try it on your own. We'll take 5 minutes and then review. Yes.
Just on your Python thing a minute ago, you got a list of tuples, whatever. Is that an alternate way? It went by quickly.
Yes.
So is that an alternate way to get the combos of rows and columns?
No, so this is what it's kind of doing under the hood. So sometimes it's a little bit confusing when, for students, when they see this kind of notation where you're specifying all the indices for the rows and all the indices for the columns. You're not specifying them as 0, 1, comma, 1, 2. Like, you're not providing them as those tuples, you're providing them as rows. Yeah, so like under the hood, for me conceptually, when I first saw this, it was like, wait a second, like I'm providing a whole entire list of rows and a whole entire list of columns.
So your zip is just
It was just a way to say this is actually what's happening underneath the hood. And a lot of the times, if I'm doing fancy indexing, I'll define rows, I'll define columns, I'll zip them together for me to look at it and kind of inspect and say, that's right, that's what I want. And then I'll provide rows, comma, columns as the actual slice. So yeah, I would usually define things like this, where I define a rows list, I define a columns list, and then I'd say, okay, let me just inspect this real quick. Okay, yeah, that looks right. And then I would provide it in as a rows, comma, columns, and get that. Is that me? Excuse me. Is it me on the mic? The mic? Okay. Okay. How do we do? Who got both? Good job. Okay. In the interest of time, we're going to review now because we have a longer exercise that I want to have you work on. So we're going to go ahead and review. Slide 18. Have this array. Going to reshape to 5 by 5. So we can go two different ways here, right? If I went from so if I said blue, whoops. If I said blue from left to right, we'd expect to get back 10, 6, 3, 19, right? That should be our answer. So the way I like to do this is I like to say, okay, what are my rows? If I'm going from left to right, so I want 10, 6, 3, 19. I'm going from left to right. My row is going to be index 2, 1, 0, 3. 2, 1, 0, 3. And my columns are going to be 0, 1, 3, 4. So if I say A, rows, comma, columns, rows, 10, 6, 3, 19. Okay. Do I need to go from the top down, or are we okay there? Good? Okay, what about number 2, divisible by 3? Any ideas? Any takers? Bueller? Good. Good. That's right. So A mod takes the modulo, applies it to every element of my A. A mod 3 equal to 0 is going to tell me when I don't have a remainder dividing by 3, which means it's divisible by 3. So I could create this mask, and then I could take A of that mask, or filter A by that mask. That gives me everything divisible by 3. I could have also said A where A mod 3 is equal to 0 and put it directly in there. Now some students say, well, this is great, but you're only giving me the location. You're only giving me the values. What if I wanted to keep the same shape of A, but somehow identify where those were? There's something called where. We'll talk about that, np.where, where you can provide a condition. So np.where A mod 3 is equal to 0. These will give me the locations of where that's true. But I can also provide, if this condition is true in my original array, fill it with this value. If not, fill it with this value. So it gives me the ability to apply a logical expression to A, the filter, and then what return values that I want. If true, give me a 1. If false, give me a 0. Or I could say, if true, give me a 99. If false, give me a 13. As opposed to just filtering A and getting the actual values out. So sometimes people want to know how to do both of these, which is helpful. Okay here? Okay, we have a break at 10:45. We're going to work on an exercise, a longer exercise, to practice some of the concepts that we've learned so far. So we're going to work for 15 minutes, take a break, continue working if you'd like, and then when we come back from a break, we'll review the exercise. The exercise is, if you click on this folder tab, sometimes when you navigate, it takes you down a directory, so there's another folder tab. So not the big one on the left underneath the Jupyter icon, but the one under here that says filter. If you click on that, it'll take you to your root directory. And we're going to go to exercises. Now, we're going to do calc return. If you want a challenge and you are more familiar with NumPy, there's a more challenging filter image exercise that will show you, rather than brute force writing a for loop, how you can use NumPy to smooth an image rather than kind of brute force going through line by line and column by column. It's a little bit more advanced. If you'd like to do that one, feel free to. But we're going to start with calc return. There are two different options here. If you like a .py script, like you like working that way, it's provided as a script. If you like working in a notebook, that .ipynb means it's a notebook. You can open up either one you like. Both of them have a solution. They're both the same solution. We have solutions for all the exercises, so if you get stuck, feel free to look at it. But if we open up calc return, basically we have a stock price, so we're going to calculate the return. And the way we're calculating the return is taking the timestamp that you're at minus the timestamp before it, and then dividing by the timestamp before it. That's how we're calculating the return. Okay, so you should be able to do this. We have the Apple stock price from 2008. We're importing things here for you, and we have a function called load text or load txt. We'll talk about that. It's a NumPy function to load a text file as an array. But we have these prices here, which what we're going to do is calculate the return. Here's the catch. No for loops. No for loops are allowed for this exercise. Do not try to do this with a for loop. I mean, you can, but practice using NumPy. So essentially, what we're trying to do, right, is we want to take this value here and subtract it by this value and then divide by this value. So that means we want to gather everything but the last value, right? And then everything starting at the 1 all the way to the last. That'll give us an offset of 1. Rather than, for every item, take the index before it and looping over, okay? So think about that. Let that sink in. There's a little bit of Matplotlib code. If you want to do that, we'll review it. But we're going to work for the next 10 minutes or so. If you want to work through the break, that's fine. You don't have to. But when we come back from the break, we'll review this, okay? And I'm here if you have questions, if you're still having trouble with the installation. If you need to run to the restroom, that's fine. We're going to work on this for 10 minutes and then take our break and then review. Okay, we're going to go ahead and review. How do we like this exercise? Give me like a thumbs up if you liked it, like kind of if it was okay, a thumbs down if you didn't like it. Okay. So we're going to review. I know there's some Matplotlib if you're not familiar with it. Don't worry too much about it. It's just a way to kind of plot some of the stuff we're seeing. So the first thing we're going to do is we're going to calculate our returns. And if you remember from our formula, what we're looking at is trying to take the point previous to where we're at to get the difference and then divide by that point previous. So some of you might want to, I took this tutorial like 6 years ago, and the first thing I did was reach for a for loop. Like that's what I thought I was supposed to do. So it like blew my mind when I was like, holy cow, this is like super powerful to be able to do this without a for loop. So what we're trying to do from like a data standpoint, we want to take, I know if I'm looking at this point here that I have highlighted, I want to subtract the one before it, right? Just looking at the differences. If I know I'm at this point here, I want to subtract the one before it, which is this one. This one here is this one, right? I go all the way down to the bottom, and I'm going to take this value minus this value. What that means is I can collect all of these, skipping the first one, right? So I want to just take everything but the first one. I'm going to say prices all but the first one and on. Right? And then what I can do is I can take the prices, all but the last one and on, and that gives me the difference, right? So 1 and on is going from this value all the way to the end. Everything up to the last value goes from this value all the way to everything but the last one. So if I take the difference of those, it's the pairwise difference that I'm looking for. We can call that diffs. Prices, not princes. And still wrong. Now, there's a shortcut to this. Let's say you wanted to take like 2. There's a np.diff. If you didn't know about that, of prices. I need to import NumPy here. So imports in Python, you can import the actual thing, or you can import the actual function that you're looking for, or you can import the whole entire library. I imported diff here. I didn't realize it. So I'm just going to get rid of this. I didn't import NumPy as NP. But this calculates, and I can have a offset here. So a few things in JupyterLab and IPython that's good to know. This also blew my mind the first time I saw it. Are we familiar with the question mark and double question mark? So question mark will pull up the function signature, and it'll show you all the parameters, what it returns. If it's written in Python, the double question mark will actually give you the source code. So you can actually look at the Python code that is actually written for that function, source code. And if you're in Jupyter and you don't want it to run it in a cell, Shift-Tab will actually pop it open into a separate window. So you don't have to run a cell in order to get it. So if you don't know a function, you're trying to understand what the signatures are and stuff like that, it's super helpful. There's also so I've created, let's see. I created this diffs. There's a handy np.array equal function here. I'm going to say diffs, and is that equal to my diff of prices? Just to show you that this is, in fact, I keep doing this. If these two arrays are equal, it'll return true, return false. There's also, for some of you that might want to know, there's a np.testing.assert array equal and almost equal and stuff like this. This will tell you if two arrays are equal up to a certain decimal point, and if they're not, it'll give you like the average difference and stuff. So if you're trying to test between two arrays, it's helpful to know that there's actually a testing library to work with arrays. But now that I've gone down a rabbit hole that we weren't supposed to, so we have our diffs, right? We understand this. And then the last part of our equation is to get our returns. And we want that to be divided by our prices, not princes again. Okay, so our returns are those difference divided by everything but not the last one. Okay, we okay here? So we have this like pairwise comparison with division. If we wanted to grab days, this is just looking for the number of returns that we have. There's also there's a zeros array construction method. If I wanted to make this 0. Just providing an integer will give me a one-dimensional, however many zeros I want there. If I provide a tuple of shape, it'll give me that shape of zeros. So all I'm saying here is we want the days to go from 0 to 255, I think, something like that. And we want our zeros to be the same length of our returns. And I can plot these. So we want the days, and we want our returns here. And I can multiply that by 100 if I want. And that'll plot that horizontal line at zeros. Now, is anyone familiar with Matplotlib? Use it regularly? If we didn't want to do this 0, is there another idea that you have besides creating a 0 array? There's something called an H-line, axis horizontal line. So instead of plotting the zeros here, I could have said ax H-line at y equals 0. Whoops. And thank you. And again, I could say color is red, line, style, solid here. So if you didn't want to like create zeros in order to draw a 0 there, you can draw a horizontal line wherever you want, just using Matplotlib. This is a Matplotlib thing, not a Numpy thing, just pure convenience. Okay, so the point of this is to practice using Numpy. Introduce the np.diff if you didn't know that existed, and then understand that we can do this without using a for loop. Okay here? Anybody take a crack at the filter image? Okay, that's a great exercise. I'll show it to you so you hopefully intrigued by it. But what we have here is an image, and essentially what we want to do is we want to smooth an image using the center point of a pixel, the neighboring images, like the top, left, right, bottom. You can think about this brute force looping over every pixel in the image and trying to calculate it. We can do this much faster, up to 10 times faster than just looping over line by line and column by column, by collecting all the top nodes, all the center nodes, all the left nodes, all the right nodes, all the bottom nodes, and averaging them all at once. So this shows we have an image here. There's a smooth loop, which is the brute force, like for every row, for every column, loop over it, collect that pixel and create the average. And then there's this smooth where we're slicing here. So grabbing every pixel that's going to be treated as a top, as a bottom, as a left or right, as a center, and then taking the average of those all at once. It's like 10 times faster. And so if you're curious and you want to time it and you want to go through that, you can. It's a great exercise to kind of solidify some of these things. Okay. All right, so we're on slide like 19. I'm going to try to get through. We have about an hour, about 50 minutes left. I'm going to try to get through as much as I can. I'll stay after if there's anything we didn't cover that you have questions on. But we're going to talk about briefly some array construction methods that we've seen, and then we're going to move into mathematical operations, essentially how we do them on Numpy arrays. So for these next slides, because we've seen them, I'm going to annotate them. But if something if you'd like an example in code, feel free to raise your hand, and I can code something up quickly for you. So our array construction examples, we've talked about the ability to define a data type. So we can specify our data type. We talked about this idea of like a numerical tower. In this case, we're providing integers here and one floating point value. So it's going to promote all those integers and store the metadata, the type of items that's going to be stored in that array is going to be that floating point value, right? We've seen this. If I want to specify the data type at array creation, I can use the keyword parameter dtype, right? So I'm saying np.array, providing the numbers that I want, and then providing the dtype. If I have an existing array and I want to create a new array, but change the data type or override that array with a new data type, I can use the .as type. Right? Maybe it'd be better if I wrote this. .as type. So a equals a.as type and provide a different value in here. There's a lot of different types of, there's a lot of different NumPy types. So we've looked at 64-bit integers, there's 32-bit integers, there's 64-bit floats. There's also something called like an 8-bit unsigned integer. This is very common with images. So if you think of like your RGB scale, those images are from, or those numbers are from 0 to 255. Those are called unsigned 8-bit integers, which means for every item you have 8 bits. So you think about like 8 different slots. It's either a 0 or 1 comparing to base 2. So that 0 to 255 is the fact that these are 8-bit integers where you can go from all of them being 0 to all of them being 1, which is 255. So that's why you have like the RGB scale, if you see on images, like 0 to 255, that's where that's coming from. But there's that type in NumPy. And we can get all that access to the data types and the number of bytes using that metadata that we've seen before. Okay, we've used a range or an array range to provide a start, a stop, and a step. You can also provide the data type. Remember, if you provide an integer, it'll return to you integers. If you provide a float, it'll return to you floats. It tries to infer that data type for you. So in this case, our array of integers, 0 to 3, up to not including. We can also specify different intervals. This is like every 4th pi, essentially, is what we're doing here. 0 to 2 pi, every 4th pi is what's happening. Now, there's a warning here. It says be careful. Typically, we say that this is up to not including. So you'll notice here that this is not adhering to that behavior. It's including the top value here. So it's a little bit dangerous, I guess, in a sense. The documentation says instead of using np.arrange, if you have a non-integer step, there's something called lin space, linear space. So you can use the linear space to actually specify whether or not you want the n to be included. What's happening here is we have floating point arithmetic. It's not as precise, so you're still getting the value, the top value. There is a ones and a zeros array creation. So if you want like a bunch of ones, you can say np.ones and provide the shape. If you want zeros, there's also an identity. So MATLAB users EYE, right, I think, is the identity in MATLAB. But there's a dot identity, I think, on the next slide. Yeah. So we can provide an identity, right, and that's just along the diagonal ones. Everything else is a 0. You can provide, the default is floating point, but you can provide like integer if you want it to be an integer for those array creation. And then we have, sometimes you might want to like instantiate an empty array and fill it as you're potentially like doing calculations with another array. There's a ways to do np.empty or empty like. So if you have an array that you want to create an empty array like. Now empty doesn't fill it with zeros. Python does something, it has a garbage collection that manages memory in the background for you, so you don't have to allocate and deallocate memory. Empty, I believe, works where it fills that array with things that have just recently been garbage collected. So it's not filling it with zeros, it's filling it with things that were recently garbage collected. But you can create an empty or you can create zeros, and then you can fill with a value, or you can use .full, which will create a full value if you want to. Rather than taking an existing array and filling in every element, you can just automatically create a full. So this is saying we want 2 values filled with 5, but we could say 2 by 2 and say 5, and it would create that 5 by 5, or 2 by 2 with 5s in there. So we have this idea of empty, we have this idea of full and fill. We have identity, .ones, .zeros, various array creation techniques if we want. So there's something called lin space and log space. So this creates from a start to a stop. So linear space is going to give you, so this is the start value. This is the n value, and this is the number of items. So this will create 5 items linearly spaced from your start to your stop. So this is helpful if you want to be able to like plot something or like be able to do some type of analysis where you have 2 intervals and you want evenly spaced things to check things at or plot things at. So it's linear space. There's also a log space. The default is base 10, but you can, so this is saying 10 to the 0, 10 to the 1 in log space, or you can change the base and you can make it. So this is from 10 to the 0th, 10 to the 1 power is what that log space is doing. 5 of those, and the default is base 10. But you can change the base to 2 if you wanted to. Okay. There is a np.load txt. Who's used pandas before? Probably like the first thing you learn in pandas is like read CSV, right? pd.read CSV. NumPy has a similar concept. It's load txt, not load text. I can't tell you how many times I type load text, txt, but it gives you the ability to take a text file and load it in immediately as an array. So this is nice and convenient. If we had this text file up here, data.text, we have different parameters where we can say skip rows, so the number of rows you want to skip. That'll ignore this first one, beginning of file. You can say what you want the data type to be returned when you get it back as an integer. You can specify whether it's comma separated. I think the default for this is white space. So you have to specify this if it's CSV or comma delimited. There's a use column, so if there's a column that's wonky or you don't want, this is saying only use 0, 1, 2, and 4. So we have dates in here, 0, 1, 2, 4. It would eliminate kind of the third column. And then there's also a comments, so you can provide a single or a list, and anything that starts with this or has that gets treated as a comment, and it will get thrown out. So essentially, it will load this in as an array for us when we specify these different parameters. It's much like pandas read CSV. And then if you have an array, you can use np.save txt to save it as a text file, provide the name, and you can load back and forth between the two. If you would like practice, we don't have time for it today, but in exercises, there is a load text. Again, there's a solution for each of these. We have some very simple text files for you to practice reading in, one more complex one, and basically helps you. The way I do this is just start with the file name. You might get lucky and it might read it in as an array and not give you any errors. Oftentimes you get back an error that's saying like, hey, there's a like parenthesis or like this weird like parsing that's going on. So you might need to skip a row. And then if you get this kind of other file here, you can start trying to provide some of these other parameters to actually read it in. So there's a solution here for load text if you want some practice there to show you some of these things. The head function is really good. This allows you to like read the first like 3 lines of a file. If there's like a file that's giving you trouble, rather than like say it's like 1,000,000 lines and you don't want to read it in because it can't fit in memory, you might want to read like the first 3 lines. There's a little Python function. You can use like cat or head from the actual command line, but it's a nice little Python function to help you here if you're curious. That's not NumPy. It's base Python. Anyway, it's a good exercise if you're looking to practice reading in text. Okay. So some of the, we're going to talk about doing computations with arrays. There's 4 main rules that we have to be aware of when we do computations. If you come from the pandas world, these are different. So pandas does something called automatic like data alignment, where it's going to try to align on the series. If there's not the same shape, it will not propagate null values for some of the reduction techniques. So this is a little bit different if you're coming from the pandas world. For NumPy, our first rule is we're always going to check whether or not objects have a proper shape match. So if we have one shape that has 3 elements in it and one shape that has 2 elements in it, we can't add those together. It's not going to be able to add those together. The stipulation exception with this rule is a scalar. So you have a scalar value and you have like a multidimensional array and you add that, it will propagate that all for you. There is something called broadcasting that hopefully we'll have time to talk about. If one of these indexes is a 1, NumPy will essentially stretch that across the other indexes for you and actually add those together for you. There's a slide later on, we'll talk about that. But for now, type shapes are checked. You need to make sure that shapes match when you start adding things together, because remember this concept of vectorization, it's trying to do that in an element by element fashion. And when you don't have those things, those shapes don't match, NumPy doesn't know how to handle that. The second thing is these mathematical operations apply element by element, right? If we had A and B and we were adding those together, it's kind of like zipping them or stacking them on top and adding them. Rule 3 is a little bit of a gotcha. Remember when I said we had a 2-dimensional array and I said there was 3 ways to calculate the sum? You take the sum of everything in the array, you take the sum across all the columns, 1 per row, or you could take it across the rows, 1 per column. Reduction techniques like the mean, the sum, where you're trying to condense things down, will always be performed on the entire array unless you specify an axis. Okay, we talked about the axis being 1 and 0 and 1 for a 2-dimensional case. So I have this array. Let's do 6 by 4. If I say dot sum here, it's going to take the sum, or I could say np.sum of A. It's going to take the sum of all those values in my array. But if I specify an axis, it'll sum just for those. So notice here I get 4 values. Axis being 0, going down. So across my rows, 1 per column when my axis is 0. When my axis is 1, I'm going across my columns, 1 per row. Okay, so a way to think about this, if you've never encountered this before, is if you take the shape, the axis that you specify will disappear in the reduction. So axis 0, what's at 0? That's 6. That goes away, so I'm left with a 4. If I specify axis 0, this is going to go away, so I'm left with 4 values. My shape here, if I specify axis is 1, what's at 0, 1? That's a 4. These are going to go, that 4 is going to go away, I'm going to get 6 values. So you can think about it that way, or you can say a.sum axes, you can cheat. Take the shape of that and see if it's what you want. Now this doesn't work if it's a square array, but this does work if it's not the same, right? Is this okay? Make sense? So this is a little trick to help when you start doing computations. You have 6 by 4 array. Okay, I want 1 per, I want 4 values. Which one do I need to specify? Which sum? Or which axes, I should say, for my sum. Okay, so we have to specify an axis. And then the last one, missing values. So there's an np.nan, not a number. So missingness is encoded in NumPy. Missing values propagate unless you use something called a nan sum or a nan mean or something like that, which ignores null values. So in NumPy, if I had 1, 2, np.nan, 4, a.sum, a.mean, these are all returning a null value, because this nan, this null, gets propagated through that calculation. But there is a nan sum or a nan mean that will calculate. Now notice this is 1 plus 2 plus 4 divided by 3. Right, that's what we want. We don't want this divided by 4. So it's correctly ignored in the numerator and the denominator, I guess is what I'm saying, right? It throws it out, it ignores it completely. So if you have null values and you need to keep them in your arrays, if you do any type of reduction technique, that null value is going to propagate through and you're going to return to null. But there are things like a nan sum, nan mean. Now you'll notice I'm calling things sometimes with a dot sum. There is no nan sum. That has to be called from the top level NumPy. So some of these are accessed at the top level as a NumPy function. Some of them you can call them as array methods. You okay here? Okay. Multi-dimensional arrays. For right now, I want you to pretend, don't look at the bottom of this slide. When we have multi-dimensional arrays, this is what I was talking about before. When we add a dimension to our array, it goes to the beginning of the shape. So what's happening here is if we have just 4 values, we have a vector, we would say that this is our 0th dimension. We have 1 dimension going this way. That's our 0 dimension. Essentially, the axis equals 0, and we take the sum or something across this way. If we now add 2 rows, that 4 in my shape, so think of this as your shape tuple, that 4 gets bumped over to the 1. How do we represent that from like a coordinate standpoint? We add 1 here. So now the axis going this way is a 1, and the axis going down is a 0. Okay, so we've appended to the beginning of the shape tuple and shifted everything to the right. If we go to 3 dimensions, that 2 and that 4 shifts to the left, so we add 1 here, we add 1 here. That now becomes a 2, and that becomes a 1. And our 0th dimension is into the screen. So we've appended at the beginning, we're going into the screen. So what that means is taking the sum or the mean and specifying axis equals 0 from a 3-dimensional case is going to sum in the screen, into the screen. Axis equals 1 is going to sum down across my rows 1 per column, and axis equals 2 is going to sum across my columns 1 per row. Trigger warning. If we're in 2 dimensions, axis 1 sums across my columns 1 per row, and axis 0 sums across my rows 1 per column. This is different depending on how many dimensions your array has. Because of that reason, you might see people that are working with higher dimensional arrays always use negative indexing. That's because the negative indexing starts counting from the back of your shape tuple. If you remember, we're always shifting our shapes to the right, which means you're always going to start counting from the back. So if you specify axis equals -1, you're always going to be summing in this direction across your rows 1 per column, no matter what dimension you're in. If you specify -2, you're always going to be summing down across your rows 1 per column. Did I mix that up? I think I messed that up. -1 will always sum across your columns 1 per row. -2 will always sum across your rows 1 per column. -3, if it exists, will always sum into the screen. And -4, if you have that. My mind doesn't really grasp 4 dimensions as well. But you have like these blocks, right, where you have 3 dimensions and you have different blocks. Maybe you have like a time dimension or something. It'll sum across your blocks in that aspect. So sometimes you might see people specify the sums or the means or the reduction based on the negative indices, because -1 is always going to grab from the back of that shape tuple. But if I said in 2 dimensions versus 3 dimensions, axis 0 is a different concept as far as the sum and the reduction goes. Okay, here? Okay. So slide 27, when we start actually defining some of these, we have a two-dimensional array, right? Our axis 0 and our axis 1, or axis -2 and -1. If I say a.sum, that's going to be 1 plus 2 plus 3 plus 4 plus 5 plus 6, right? I haven't specified an axis. But if I say axis is 0, I'm going to sum across my rows, 1 per column, down the 0th. If I specify a 1 or a -1, I'm going to sum across my columns, 1 per row. Okay. So we have a bunch of other methods that we can call on arrays. So we have the sum, we have a product, so we can do the product across all of our values. There's a min and a max. There's something called a standard deviation of variance. We have our mean. There's something called P2P, or peak to peak, which is the max minus the min for all of those. So we can do that as a method on our arrays as well. So one thing that's helpful here, let me actually code this. It's a little bit easier to see. So slide 29. There's a 2, 3, 0. Whoops. So I have a two-dimensional case. If I take the min, so I can say a.min will give me the minimum for the whole entire array. Say a.min axis equals 1, and that'll give me the minimum for each row and each column in this case. There's a max, there's a min. There's also something called the Arg Min or the Arg Max. So sometimes when we're doing computations, we don't really care about the min or the max actual value. We care about where the min or the max value is. So there's something called an Arg Max. But this is a 1. Why is that a 1? What's happening is an Arg Max behaves on the flattened array. So if we flatten this, this tells us that our maximum is at the index 1 here, based on a flattened array. That's not really helpful, right? We run it in the original shape. So there's something called unravel index. Unravel index. And I can provide the location that I want in terms of a flattened array. So this is a 1. And then the shape that I want that to convert that into. So a.shape. And this will tell me this is at row 0, column 1. So it converts the actual, it undoes the flatten essentially and gives it to you in terms of the coordinates of whatever you're providing. So my A is 2 by 2. If I just did the arg max, it tells me 1 because it's saying flatten it out and it's giving me this. Well, I don't want 1. 1 doesn't help me if I'm trying to find it in terms of my original array. We can unravel it in terms of here, 0, 1, and it shows me 0, 1 here. So that coordinate. Put it in the right coordinate system, if you will. Okay, there's also something called np-where. We've seen that before, but I'm going to demo it again here. Let's see, -2 to 2. Square this. This is slide 30. So we have this array. I can create a mask here that is where a mod 2 0. So I have my mask. I can say a dot where that mask is true. This will give me the np dot where mask. Sorry, let's try that again. I have this mask, it's Booleans. Say np.where, based on that mask. It's going to tell me the locations of the true values. So np.where is going to accept either a Boolean mask or a condition, right? Condition of trues and falses. And it'll tell me where those things are true. Notice that this is a tuple. So if A was equal to np.where A is less than 2. It's a tuple because it's giving it to me in terms of the shape of my arrays. It's a two-dimensional array, so it's giving me in terms of my different values. This is the first row, column 0, the first row, column 1. So it can tell me where things in my array are located, but it also allows me to reconstruct an array like we saw before. So if I had A is if I had A here and I said np.where A mod 5 is 0. This will give me the locations of where that's true. But if I provide something else in here, that whole entire first column is the only place that it's divisible by 5. And I'm saying where that's true, give me a 1, else give me a 0. So it allows me to fill in for that Boolean mask essentially as well. Okay. If I have my array of 1, 2, 3, 4, 5, 6, we have the mean. Again, I can specify an axis of 0 or an axis of 1. We also have a standard deviation and a variance. All right, so this same with my variance. Any statisticians? I think we can provide the degrees of freedom, if I'm not mistaken. So it treats this as the actual population. So if you're doing any type of like statistical, you want to treat this as a sample, you can change the degrees of freedom to 1 if you want. But again, I'm calculating that axis equals 1, but you can do the whole entire array or column or row wise. Okay. So if we give it a try here, copy and paste this. I'm not sure if this is in our notebook? Okay, it is. So you can do this in the notebook here. Want to grab the maximum of each row, the mean of each column, and the position of the overall minimum. Okay. So let's take 5 minutes, we'll do that, and then review and continue on. Okay, we're going to go ahead and review. So we have our array A. The first thing we want to do is get the maximum of each row. So if you look at our shape, if we want the maximum of each row, how many values would we expect to get? 5 or 6? 5? 5? That's right, 5. So what we want to do here is if we want 5 to remain, that little trick is, okay, I want the 6 to disappear. It's at axis 1. So I would say a.max axis equals 1. That'll give me my 5 values back. Again, if you aren't sure, you can always do something like this. If it's not square, right, and say, oh, okay, that's the right one. That's the one I want to use. Axis equals 1. Or you can look at the shape and say, I want this one to disappear, so I'm going to specify axis equals 1. Okay, so that's the max of each row. Then I want the mean of each column. So it's going to be axis is 0. So I get 6 values there. And then I want the position of the overall mean. So or the position of the overall minimum. So there's a few different ways to do this. So the first one is I can say np.arg min of A. Well, that's not very helpful. It's just telling me in terms of A.flatten, it's at the 15th index. So I'm going to say unravel index A.arg min A.shape. If I look at A, row 0, 1, 2, column 0, 1, 2, 3, is that 0? So option 1, I can use unravel index. Option 2, I could have said np.where. If I knew the minimum was 0, I could have said where A is equal to 0, and that'll give me the location. Or I could have said where A is equal to the min. Oops. Okay, so you can use unravel with Arg Min. You can use where. Did anybody do this a different way? Or think of a different way we could do this? If I took the min and then took the min of that, Arg Min. And I took the min of each column. Whoops. So if I take the minimum and then take the argument minimum for each row in each column, you could do something like that as well. All right, so this is my row index. This is my column index. Take the minimum for every row. Take the minimum for every column, and then find which argument is in there.
Just to comment that these three methods give the same result if there is only one minimum, but they could give different results if there are multiple minimums.
Yep. So let's say so np.unravel. This is only giving my first occurrence. This will give me all of my occurrences. And if I did this trick, it's only going to give me my first occurrence. Thank you. First occurrence. Reverse. Yeah. But where will give you all the locations. Okay, questions? Okay here? All right, I'm going to try to do a flyby on broadcasting. The last 10 minutes, there's the exercises directory has some really good exercises for practice outside of the course. They all have solutions, so if you're looking to try to brush up on some of these things or see how we actually use them in practice, they're real-world examples. They're great to go back and look at, and they all have solutions, so feel free to look at them during lunch or during your time here at some point. So array broadcasting, a lot of the times in NumPy, we can think about this like vectorization, where we want to do element by element calculations. Well, instead of always having to create the same kind of shape, if we want to do larger operations like a 4x3, we don't have to create this 4x3 in order to add these together. If one of these has a dimension where there's a 1 in them, oh, I'm sorry. Thank you very much. Thank you. Sorry about that. So slide 35. I kind of hinted at this before, but if we have, the easiest way to think about this is if we have two 4x3 arrays and we add them together, it's easy to see how NumPy is just going to take both of these, you can like lay it on top of each other and sum them to get a 4x3 output. If we have this 4x3 and another matrix or array that has 3 elements, we can describe this as 1, 3. What NumPy is going to do is stretch that in the other element for us so that we get back a 4x3. So we don't have to create another 4x3 or take our existing array that has 3 values and create a 4x3 by repeating those. Numpy is going to handle that on the back end for us and do something called broadcasting, where it's going to stretch this across without copying any data and create that 4x3 array for us. And the reason this is very powerful is because we could even have a 4x1 and a 1x3, and that's going to stretch this out and stretch this down and give us that same 4x4 array. So Numpy is going to try to do this optimization on the back end for us if the shapes allow for it. So it's not going to copy this information over. We don't have to repeat certain things. It's going to try to do this for us, which is really convenient and really nice when we do mathematical operations. So visually, this is kind of what's happening. The rules essentially is if the trailing axis, so it always looks from the back, from right to left as far as the shapes go. So if the trailing axis is a 1 or they have the same, broadcasting can occur. So in this case, what's happening is we have a 4x3 and a 4x3. That checks out. That's fine. We have a 4x3. The trailing axis for this, 1x3 or 3 comma, is a 3, which matches this 3, so it can be broadcast. This is a 4x1. This can be, because this is a 1, the trailing axis, we can stretch this across and stretch this down to get our 4x3. So the idea here is they must be, the trailing axis, and one of them can be 1, the smaller array, and they must have the same. If not, we won't be able to broadcast. So the idea here is we have a 4x3, and this is a 4. So what's happening here is this last axis, this isn't going to work. There's no way to broadcast that down and add those things. So one nice way about doing this is there's a np.newAxis. We can take this shape currently is 3 comma. Whoops. So slide 37. A is np.array 0, 10, 20, 30. B is np.array 0, 1, 2. A.shape, B.shape. I can say B.reshape to make this 1x3. Or I could say B np.new axis, everything in that direction, my old direction. We can reshape it this way. If I try to add A and B, it's telling me it's not going to be able to add those together because we have a 4 and we have a 3 comma. But if I make B now I have a 1 here. Whoops, did that backwards. The last column, the B. Now that I've thoroughly confused you. You have A, you have B. I've essentially converted that so it's a 3x1. So I've stacked this in column. So I have 4 as my A. I have 3 going down. That's going to stretch each of those across to give me C. Depends how I want to. On the slides, they did A. Maybe I should do it that way. We have A. We have B. We're saying Y is equal to A np.newAxis plus B. Keep doing this backwards. The trailing. So if I look at this, this is converted my A. Kind of stood it up. So it's taking that, stretching it across, stretching my b down, and adding those together. So this is helpful when we start doing things. If you've used NumPy before, there's something called a mesh grid. So you might have seen this where you're taking, like, given an array of x, that's most famous or most widely used in plotting, where you have, like, given an x array, given a y array, create a mesh grid where you're having one point for all of those, like pairwise, all of those points across. It's a mesh grid, but that will sometimes copy your data and not be as memory efficient. When you do, you can do the same thing with broadcasting, which isn't going to copy your data and is a little bit more memory efficient. So these two things on the same slide do the same thing, where the mesh grid is taking 1 and 2, 3, 4, and 5, and essentially giving you all those points and then taking the sum, whereas here we're creating the new axis and allowing NumPy to broadcast that for us. So it's a way to do kind of the same thing in some regards. I want to, we have 3 minutes left. I want to move on. The last thing I want to talk about is kind of the memory buffer. So there's, in the universal function, there's things that all universal functions share in NumPy. There's a dot reduce, there's a dot reduce at, there's a dot accumulate. And on these slides, these serve as kind of a reference point to show you how those kind of work, where reduce is going to reduce those things down. It's like a sum. It works the same thing as our sum. If you wanted to see accumulate, gives you kind of the intermediate step. So reduce would give you just everything summed. So here, 1 plus 2 plus 3 plus 4, it's going to reduce that down to one number. Accumulate is going to give you the intermediate steps. So 1 plus 2 is 3, 3 plus 3, 3 plus 2, down the line here. So 1 plus 2 is 3, 1 plus 2 is 3, 3 plus 3 is 6, and then 6 plus 4 is 10. It gives you like the intermediate steps if you want to do some type of accumulate or something like that. There's also a reduce at, so you can specify specific indices of where you want to like reduce things at, not just the whole entire array. So if you had these indices where you had like monthly values where you wanted to condense them down, you could do something like that. But the last thing I'm trying to squeeze in here is how NumPy handles this memory block. And this starts to make sense why things are designed the way on the back end from NumPy, from a like view and a like copy standpoint, if we think about the way NumPy stores this. In kind of memory world, there's no idea of like a multidimensional array. So when we think of something being 3 by 3, in memory, this is just like a contiguous block. It's just storing the data there, and we have a reference to that. So we need some way to be able to say, hey, for us as developers, this should be 3 by 3. So we need some type of metadata to describe the data buffer and then convert it to like what we expect as like a 3 by 3 array. And we do that through the metadata. And that metadata, we have dimensions, shape, and then strides. These strides are what determine how our array like visually is displayed like to us, our understanding from a Python view. So this in memory land, you have this contiguous block, but when we say the strides are the number of bytes that you have to skip over in each dimension. So what we're saying here is that when our strides are 24, this is our dimension 1, or remember our rows. So to go from one row to the next row, I need to go from 0 to 3. How many numbers is that? That's 1, 2, 3 numbers. This array, we're saying, stored 64-bit integers. Remember, 8 bits is 1 byte. So if we have 64 bits, it means we have 8 bytes. So we have 8, 16, 24. It has to skip over 24 bytes to go from one row to the next. Okay? If we want to go from 3 to 6, go to that next row. We're going from 3 to 1, 2, 3. Right? That's 8, 16, 24. In terms of columns, this is dimension 1, right, this way. So we need to go from 0 to 1. That's only 8 bytes. So this strides here tells us how things are getting mapped. And this is why a transpose is a very, very cheap operation, because it's pointing to the same exact data buffer. All you have to do is flip the strides and flip the shape. So you don't have to change anything as far as a NumPy array goes. You're changing the metadata. When you call a.t, a transpose, you're just flipping those two things. That's why it's very, very cheap. And that's why anything in NumPy, when you start reshaping things, is a very cheap operation, because it's just changing the metadata. It doesn't have to create a whole nother data buffer and all new sets of data in order to create that. Okay? So I know that was like 100 miles an hour. I know that was like very, very quick. But it starts to make sense why NumPys behave the way that they do sometimes when you understand kind of how the data is stored. Okay? We're 2 minutes over. I apologize for having to go through that very quickly. I'll hang out if you have any more questions or anything I can clarify. Again, the exercises are a great resource outside of this class. I'm going to save my history, so everything that I typed, all my typos included in the IPython shell, I'll upload so you guys have access to that. But thank you so much for a wonderful tutorial. I appreciate your engagement. Thank you all. And you are free. Have a wonderful SciPy too, by the way, for all of you that it's your first time. Hopefully this kicked it off right. So welcome. We're glad you're here. Thank you so much. And I'll be here if you have any questions. Thanks.